and welcome to Car Corner. My name is Richard Saxton. I'm the coordinator of the automotive programs here at the Community College of Philadelphia. In today's episode, Dan Reed is going to get your engines revving with his discussion on base engine testing. If you have any questions about the automotive programs here at the college, please check us out at the website. Okay, now it's time to get your car in gear.
Hi, I'm Dan Reed with Community College of Philadelphia. Welcome to Car Corner. Today, we're going to be talking about what happens on the inside of an internal combustion engine. More specifically, what happens when parts fail and really why the mechanical parts inside an engine break and what happens when they do break. And it's interesting to note that all of the layers of the electronics that modern cars come with today, at their core, they still share the same exact basic parts that the original internal combustion engines did from the very first automobiles and gas engines ever produced. The fact is that those core parts still don't actually have any electronics attached to them, and we can actually use the world of physics at our disposal to measure, to determine whether or not those components are functioning properly. So first, let's talk briefly about some of the basic components that are inside a four-cycle internal combustion engine. What we have here on the bench is this is what's known as a cylinder head. Now, a cylinder head is a large metallic component that sits on top of the engine block assembly. Inside the engine block assembly, we have things you may have heard of before, pistons and a crankshaft and an oil pump and things like that. Cars still have them, and they've always had them. The cylinder head itself contains components like camshafts and valves. Those are other components you may have heard of as well. So this type of camshaft is what's known as an overhead camshaft, cylinder head. What it is it's, first of all, it's made out of aluminum. They used to be made out of cast iron. Today, since probably the mid-1970s, manufacturers started making them out of aluminum because it was lighter weight. And anything that saves weight helps save fuel, which makes cars faster and more fuel efficient. So our cylinder head itself is made out of aluminum, which is a relatively soft, a weak metal when compared to things like cast iron. But it works great and it's where it's located. It doesn't get too hot and it's cooled pretty well. These components here across the top, these are what's known as valve springs. Now, valve springs are attached to valves, and I got a couple valves here. The valves themselves can come in different sizes depending on the size of the engine, and if it's a different type of internal combustion engine, like say a locomotive, a diesel locomotive, or a tugboat or something like that, the components just get larger as those engines physically get larger. If we have something small, like a lawnmower perhaps, the components just get smaller. So they're pretty scalable for a lot of different cars. And valves generally work pretty quietly. They don't really do much of anything in terms of the way of having explosive forces occurring inside of them. But what they do is they allow an open and closing of the cylinder head to allow fresh air in and exhaust gases out. And one of the things that can happen with valves is that the valves themselves can actually bend. And if you've ever heard somebody say, oh, well, the cylinder head has a bent valve, that's what a bent valve looks like. The valve is supposed to slide up and down in a housing called a valve guide. And if the valve gets bent, it can't slide anymore. And likewise, if it's sliding up and down like this, it's not closing properly against its sealing surface inside the head. If we look at the underside of a cylinder head, we can see the undersides of these valves. And cars typically are going to have at least two valves, sometimes more per cylinder. And on this engine, we have intake and exhaust valves. And the way this engine is laid out, these guys are actually I believe these are the intake valves and these are the exhaust valves. The shape on the underside of the cylinder head is dictated by the engineering requirements of the car, what type of car it's supposed to be, the fuel economy it gets, that type of thing. Hot rodders like to modify this area of the cylinder head, so when they talk about doing cylinder head work, this might be one of the areas. By changing the shape of this, we can change how the combustion process happens, when it happens, and that type of thing. So these valves open and close, and this valve right here is in a open state. the valve itself is off the seat, and with the cylinder head on the engine block deck with the valve open, what that's going to allow is that's going to allow air in or out of the combustion chamber. This round area right here is where my pistons would be sitting. So the pistons are going to come right up against the underside of the cylinder head, and then they're going to allow air in and out through these valves. So a couple things worth mentioning about the cylinder head and the valves while we're here. You can see this residue on the cylinder head, and what this is this is residue left over from a component which separates the cylinder head and the block assembly, called a head gasket. A head gasket has a really, really difficult job because not only is it making sure that the cylinder head seals against the engine block, but you can see also that there's these holes and ports all around here. And what we have is sometimes we'll have oil or we'll have coolant passing in and out of those ports as we lubricate components or cool components. So a head gasket is an important part. It's really a sealing surface, but it also helps separate and make sure that we don't mix and combine coolant and oil. Oil being oil and coolant being mostly water, oil and water don't mix, and we certainly don't want that mixing inside our engine. When you have a cylinder head gasket fail, you have to remove the cylinder head. Generally, we have to clean the cylinder head and inspect it. And that can be a pretty big job. Removing a cylinder head from a car is time-consuming, and it can be a long and expensive process. So we try not to have too many cylinder head failures in terms of head gaskets. All right, so the other component, I'm going to swing this around here, I'm going to point this around the front, is we have this cog on the end of the cylinder head. This is attached to the camshaft in the engine. And normally we'd have a rubber toothed belt that would attach this cog on the camshaft down to another cog on the crankshaft of the engine. So as the crankshaft turns, it's going to actually be connected to the cog of the camshaft, and that in turn is going to help us open or close our valves. So before I get too deep into the rest of the engine functions, I want to go over exactly how an internal engine works. So let me grab a couple components here, and we'll set this up here on the bench. And first we're going to have our piston, and the piston is going to be in the lower half of the engine in the block. And then we're going to have two valves. I'm going to have an intake and an exhaust valve. And what I'm going to do with these is I'm going to talk about how the engine functions. So what we're going to do is sort of have a little diorama here set up. Air and fuel are going to have to come into the engine. Now, the piston is going to be able to travel up and down in its cylinder, and these valves are going to be able to open and close, and then we're going to have a spark plug there in between the two. And the first cycle out of a 4-cycle engine, which is another term you may have heard of before, there's 4 cycles to actually get the piston to do any work. So the first cycle is known as intake. And what we do on the intake cycle is we open our intake valve, and the piston is at what's known as top dead center. It's the highest the piston goes inside the block, and the piston starts to get drawn downward by a crankshaft. The crankshaft works just like the cranks on a bicycle. If you could imagine your feet literally being the pistons, as you're turning that crank, you're turning that center bar, and that's actually going to ultimately be attached to the transmission and drive the wheels of the vehicle. So our piston goes down, and as our piston goes down, it creates a negative airspace, a vacuum. And with the intake valve open, what we're doing is we're going to take in a nice gulp of air and fuel. And we're going to have another component which is going to be on the back side of the intake valve, and that is our fuel injector. So the fuel injector is going to spray some gasoline when that valve is open, and it's going to get sucked into the chamber, the combustion chamber of the engine. At that point, once we have the piston all the way at bottom dead center, this section is now filled with a volatile air and fuel mixture. But it's not quite ready for prime time yet. We really have to compress that air-fuel mixture to really extract that energy from it. So as the piston starts to travel back up, what we do is we close off our intake valve, and I'm going to take the fuel injector away because we don't use that anymore at this point. And the piston's going to travel up. As the piston travels up, the next cycle is what's known as compression. and that's when we compress our air-fuel ratio. Now, I've squeezed this air-fuel mixture, and when I squeeze it, it gets very hot and it's very volatile. And when people talk about compression ratios in engines, literally the amount that we compress the piston as it comes up, as we compress that air-fuel mixture with our piston, that volume of compression is our compression ratio. Once we get this as high as it's going to go, we're going to light off our spark plug. And at that moment, right then, we start to create a flame front from our spark plug that's going to travel down up against the crown of our piston. The piston at this point is now in the power stroke. We have a controlled burn that's going to actually force the piston back down, and that is the only point at which out of the 4 cycles we do any work. That power stroke is what actually produces the energy to force the piston back down. Once we have the piston all the way again at bottom dead center, the piston has to travel back up. And the reason why is because we actually have a bunch of exhaust gas now in the cylinder. We have to evacuate that gas. So the last stroke or cycle that we have is what's known as the exhaust stroke. The piston now is at bottom dead center, and what I have is I have a cylinder full of exhaust gas. What I'm going to do is I'm going to open the exhaust valve, and I'm going to push the piston up. As the piston travels up, it's going to push out those collected exhaust gases out through the exhaust port of the cylinder head, which goes into the exhaust manifold, and then down to the catalytic converter and the muffler and out the tailpipe. Once the piston has reached top dead center, I'm going to close that exhaust valve, and I'm going to start to open my intake valve. And at that point, the piston is going to start to travel back down. As it does, I'm going to bring my fuel injector back in. It's going to spray some fuel in. Piston's going to travel back down to bottom dead center again, and this entire cycle repeats. So the cycles are intake, compression, power, exhaust. Intake, compression, power, exhaust. Each cylinder of the engine goes through those 4 cycles of operation as the engine's running. The other thing that I can show you is that I have an engine right here on a stand, and let me bring that over so I can kind of demonstrate some of these components while they're all in motion and how they're timed together. So what I have here is this is a modern dual overhead cam V6 Toyota engine block, and it's an all aluminum engine. So the block, the lower half here is aluminum. The pistons are steel, and then we have 2 cylinder head banks right here. And what we have is, instead of a belt, this vehicle design uses a chain. It uses a large bicycle chain like link chain together to make sure that the crankshaft down here is timed with the camshafts. And while the engine's turning, you can see how this would all move in sequence. And one of the things that technicians like my students who took this engine apart and then expertly put it back together did is you have to be very, very careful when we're working with timing chain assemblies or timing belt assemblies to make sure that we get these components all lined up right. You just can't put the chain back on like a bicycle and everything will be okay. The fact is if the piston is at the wrong section of the stroke while a valve opens at the wrong point, the engine literally won't run, even though you may have put it back together correctly. So timing chain assemblies and timing belt assemblies are something that, you know, if you don't know what you're doing, you should not mess with inside the engine. And you may notice these links, these colored links here on the chain. That is designed for the technician when they go to line this up. There's literally marks that they're going to have to line up on the camshafts and the crankshaft to line up with those chains so they know exactly where everything goes when they go to put it back together. So again, this is the operation, and you can see that as I turn the crank, the chain is pushing my camshafts around and they're turning. And what I'm going to do now is rotate the engine sideways so you can see the camshafts pushing down on the valves, which is going to open and close the valves. And then what I have is I have a special camera that can show us what's happening inside the engine as I turn it, and we can take a look at it in real time and see what's happening. So let me turn this and put this guy right here. So on the cylinder head, this cylinder bank right here, this is the exhaust camshaft, and so exhaust gases would come out here. This is the intake camshaft, and what we have is we have a set of lobes. These pointy parts right here on the camshaft are what's known as camshaft lobes. They're going to swing around and push down on top of the valves and actually open the valve. So when you see these lobes up in this direction, it means those valves are actually closed. When the lobe comes around, it actually pushes down on the valve and forces the valve open, which is going to, at that point, allow an air-fuel mixture to come in. So let's take a look at that as that rotates around. Let's see how that all works. Now, while this is happening inside the engine, it's happening literally so fast that you would just see it as a blur. The other thing is we have a cover on here called a cam cover. We used to call it a valve cover. And there'd be a rubber gasket in between here. And there'd be oil slinging around on the inside of this, and that's part of the lubrication system. But let me get my borescope and show you exactly the operation of these valves opening and closing. We'll be able to see the piston go up and down inside its cylinder. So what I want to do is I have a tool called a video borescope. And the video borescope is a camera on the end of a wand. And what I'm able to do is I'm going to show you what happens to the piston on the inside of the combustion chamber while the engine is running. So I'm going to drop this in, and I'm putting this in through the spark plug port. And when we come down through the inside here, what we're looking at, that silver disc, is the head of the piston. And when I crank the engine over, we're going to see that start to come up. And when it reaches its highest point, that's what's known as top dead center. As the piston starts to drop away inside the combustion chamber, we can really start to see the entire piston. We can kind of look around and we can see a little bit of the cylinder walls inside there, and some of the other parts of where the combustion process takes place. So this tool is really useful because it allows a technician to basically look inside an engine without having to actually take anything apart. And if you had an engine where maybe there was a possible issue, this would just basically help a technician find what the problem, just verify what the problem could be. Not necessarily use this to fix anything, but just help verify their diagnosis. The other thing we can do here is I can pull this out and we can look at the inside of the intake valve. And as I crank this open, as this camshaft comes around on the top here, should be able to see those valves open on the inside, just right there. So by looking at, say the intake valve or an exhaust valve or the head of the piston with a borescope, again, it just gives the technician a good idea of what's going on inside the engine, and allows me to do an inspection without having to really disassemble the entire engine. So that's pretty useful. So now that we have a good idea of what the main components are inside our engine, let's take a look at some of the tools that we're going to use to actually diagnose an engine performance concern. In other words, what's going to happen when we go through and try to figure out what's wrong with one of these components. So now that we have a good idea of what some of the components are inside the engine and how they go together, let's take a look at some of the basic tools that a technician is going to use to determine the overall engine health or what the problem might be. Now, again, these tools go back to the first internal combustion engines, and literally if I took these tools and I went in a time machine back to 1920, I could use all of these tools on a car from 1920 and I would get pretty much the same results that I get from a car from today in terms of what I would expect and how the car would function. So you'll notice there's no scan tools here. There's nothing really fancy, high-end, expensive tools for me to plug into a diagnostic port or anything like that. When you have an engine that runs poorly, you really have to start with the basics, and that's what these tools help give me a framework, a baseline kind of the overall engine health inside the car. So the first test that we have, the first tester that I have here is what's known as an engine compression tester. And what this is this is a pressure gauge. And we screw this into the spark plug port of an engine, and then we crank the engine over, and we use the electric starter motor. And based on the amount of pressure that we develop in the cylinders, it's going to tell us a couple things. It's going to tell us is the intake valve opening on the intake stroke to let air in? Is the engine able to compress an air-fuel mixture, and if so, what is the pressure of that air that we're going to be able to compress our air-fuel mixture to when we actually look at it on the gauge? So the compression gauge is going to be able to tell me exactly how much pressure we can develop in the cylinder, specifically how much compression can we make on the compression stroke. If I can make something over maybe 100 psi, and that's what the manufacturer calls for, that's a good number. That's going to tell me that the internal operation of that cylinder is functional. The intake valve and the exhaust valve are opening and closing. They're sealing properly, and then the pistons and the cylinder walls are all in good shape as well. So that's really going to be a useful test. The other gauge that I have, which is really kind of an old school tool, is what's known as a vacuum gauge. And a vacuum gauge hooks up to a line behind the throttle plate on the intake manifold, and what it allows me to do is measure the relative vacuum or suction that the engine is developing. Now, if you remember back to the 4 cycles of engine operation, the intake stroke, that piston is coming down. It's creating a negative airspace, and we're going to draw in an air-fuel mixture. I'm able to measure that suction of that piston with a vacuum gauge. And generally speaking, a good, healthy engine while it's operating should be somewhere between maybe 17 to 22 inches of mercury on my gauge. And the needle should be steady. It shouldn't bounce. It shouldn't waver around as the car's running. If I open and close the throttle while the engine's running, I'm going to get movement on my vacuum gauge, and that's fine. But again, I'm kind of looking for a nice, steady, non-vibrating needle reading here with my vacuum gauge, somewhere between 17 and 22. If I have that, chances are that the overall engine health is really good. And in fact, if I go to actually buy a used vehicle, a lot of times I'll hook up a vacuum gauge just to kind of give myself peace of mind that I know that the internals of the engine are good. If there's a problem with an intake valve or an exhaust valve or a piston, that needle is going to fluctuate as that cylinder has that fault, and you're going to see it on the gauge. So it doesn't really tell me exactly what's wrong with the inside of the engine or which cylinder is at fault, but it is going to tell me exactly that the engine has an internal engine problem, and I have to do further diagnosis. The last gauge that we have is what's known as a cylinder leakage tester. Now this is a diagnostic tool that you have to have a compressed air source for, and I'll demo this later on the engine. But what we do is we hook up a compressed air outlet here from our air compressor in the shop. There's a regulator attached, and what we do with this end is we actually blow compressed air into the cylinder. And what this gauge over here with the red, the yellow, and the green indicates is this is the amount of air that's leaking out of the cylinder versus the amount of air I'm pumping into the cylinder. So if the cylinder isn't sealing somewhere, I'm going to be able to get a relative reading of exactly how much of this is actually, how much air is leaking out. And obviously I want it to be somewhere in the green area to tell me that the engine, that specific cylinder doesn't have a fault. So there's 2 other pieces as well, and these are just going to help me with something known as misfire diagnosis. Now this piece right here, this is a spark tester, and what this does is this end looks a lot like a spark plug. And what I do with a spark tester is I disconnect the spark plug boot from the engine, I connect it to this end of the tester, and I ground this end of the tester somewhere on the engine block. And when I crank the engine, what I'm going to see is I should see a nice bright blue purple spark here on my spark tester. If I see that, that means that the ignition system is probably functioning, and that it's going to be the reason that the engine is, the ignition system is functioning okay. So it's not the reason why the engine's running poorly. However, I could still have a problem with a spark plug, but since we're going to take them out anyway when we do a compression test, we'll see what we got there. The last piece I have, and probably the more modern piece of test equipment which I might have, is what's known as a Noid light or an injector light. What these testers do is they are basically 12-volt lights. They're very small, and we can plug these into the fuel injector harness of our car. When we run the car, the fuel injector is going to open and close and let fuel into the cylinder as the intake valve opens. That fuel injector works on an electrical signal, so if I remove the injector and I replace it with a light bulb, the light bulb should blink as that injector opens and closes. So what these allow me to do is these little metal prongs here allow me to plug into the injector harness and then actually go through and see if the injector is getting power. And if I get a blinking light here while the car is running at that injector, it means that that injector is the wiring and the computer and everything back from there is good, and there could be a fault possibly with an injector, but chances are that's not the problem. So, all right, let's take these. Let's move these tools out of the way, and I just want to briefly switch back here for a second, and I just want to talk about pistons. And going back to the piston in terms of damage. Pistons have rings. The rings are what's going to seal inside our cylinders, and these rings, generally when it's in the engine, these gaps are going to close up very tight. These top two rings, what they do is they seal the combustion chamber. This last ring, this is what's known as a three-piece oil control ring, is what helps control oil from getting into the combustion chamber. We do lubricate the cylinder walls a little bit, and this special ring acts like a squeegee. So the ring is really used to squeegee the oil back down into the crankcase. It's not used for combustion gases. Remember, the head of the piston or the crown of the piston is what we saw on the inside of that other engine, and this is where I have a lot of heat damage and things like that. This is really the part that really gets punched in the face while the engine's running. Along those lines, if we have a defect with our engine, you can see the difference. These are not from the same engine, but you can see that piston damage can definitely occur inside an engine. This engine had some mechanical damage, and we can see that the area where the rings sit, the ring is actually broken, it's cracked, and then we have all the scoring on the skirt of the piston. This engine obviously was done. It was there was no saving it at this point. You can't fix this with any type of a special additive to the oil or anything like that. This has to come out at that point and be replaced, and what we ended up doing was just actually replacing the entire engine because every cylinder in this engine looked this bad. But that happened in part because of some serious neglect on the owner's part. Basically, they ran the wrong fuel in it, and it was also had the wrong oil in it, and consequently it didn't last too long after they did that. So now that we're done taking a look at our pistons, let's take a look at the car behind me, which has a genuine engine performance problem. So what we have here is we have our Honda Accord, and it has possibly an internal engine problem. It has a misfire, which is a way of saying out of the 4 cylinders, one of them doesn't seem to be contributing any power. Now what we're going to do is we're going to run through a couple basic tests, and this car will start and run, but it runs badly. It runs poorly, it misses, it has a lack of power, and you can actually hear that the car doesn't sound right while it cranks, and consequently, if it doesn't sound right when it cranks, there's a good chance that there's something going on internally with this engine. It doesn't have to be catastrophic, but it's probably not going to be an easy or cheap repair. But we can narrow down our diagnostics using some of the tools that we've talked about from before. So let's get on with it. What I'm going to do is I'm going to turn around and I'm going to turn the ignition on. And then what I have is I have a remote starter switch here. And what that's going to allow me to do is start the vehicle from outside the car. And this is necessary when you're doing a compression test or something like that, because I have to be able to look at the gauges while the car is running, and I want to be able to start the car from underneath the hood. So that's why I have this gauge. Just remember, if you do use a remote starter switch, make sure the car is not in gear. If the car starts and runs while it's in gear, the car will literally just drive and run you over. So please be very, very careful while you're using a remote starter switch. Okay, and I'm going to start the car up. Yeah, doesn't run great. That stutter, let me shut that off. That stutter is a classic sound of an engine misfire. What that means is that one of these cylinders is literally just not doing its job. The reason why the engine was kind of jumping around so much is because out of those 4 cylinders, they're all balanced against each other, and they're balanced literally against the amount of energy that they'll produce. If one cylinder is not producing enough energy, it throws the engine out of balance, and we get that shaking roughness, which us technicians refer to as misfire. So the question is what cylinder is misfiring? And what we're able to do is we're going to do a quick test here where I'm going to unplug a fuel injector while the engine's running, and what that's going to do is that's going to determine if the engine runs any better or worse. And if the engine does not seem to change while I have that injector unplugged, there's a good chance that that's the cylinder that I can focus my diagnosis on. That test is referred to as a power balance test. Some newer cars have the ability to do a power balance test through the computer. The technician can literally command the computer to do one. This vehicle doesn't have that ability, so we have to do one the old-fashioned way. So we'll just give it a shot. The other thing I'm going to do is I'm going to hook up my vacuum gauge here, and I'm going to be able to take a look at my engine vacuum and try to figure out exactly if I have an internal engine problem. If I do, we'll just have to dig a little deeper. So let me unplug this line here and hook up my vacuum gauge right here. Position this guy. All right, I'm going to turn the ignition back on. We'll give this another try. Well, remember I talked about the needle dancing around if there's a problem? Yeah, this car definitely has something internal going on, so let me shut it off. All right, you saw how much that needle was jumping around while the car was trying to idle, and again, that is a classic sign of an internal engine problem. So what I'm going to do is the engine actually doesn't really run well enough for me to try to figure out exactly which cylinder is at fault. So what I'm going to do is I'm just going to start with a compression test. I have a good clue that that's what the problem is because of the needle movement on my vacuum gauge. So to start a compression test, what I'm going to do is I'm going to pull out the spark plug boots, and if I had to, these ones are basically installed by length, so I don't really have to label them, but if I had something like a V8 or a V6, I'd be very careful to make sure that I labeled these so they went back on the correct cylinders. I wouldn't want to mix that up. So let's get started on that. The next thing I'm going to do is I'm going to pull the spark plugs out. And when I do this, I'm going to use a ratchet and a socket with an extension and a special socket called a spark plug socket. Now, the spark plug socket has a rubber grip on the inside of it, and what it's going to allow me to do is make sure I can pick up that spark plug when it falls out so it doesn't fall down inside the tunnel that it's in. If I don't have a special spark plug socket, it's probably okay to still use another socket, but these are pretty inexpensive and they do a great job. They can be a little difficult when you go to reinstall the spark plugs when we're all done here to make sure that everything's lined up. Sometimes you can use a magnet or a piece of vacuum hose to pull them out or put them back in, but we have the right tool, so we'll use that. As I do this, if this area of the engine was really, really dirty or anything, I'd actually want to blow this out maybe with some compressed air to make sure I didn't have any debris fall inside the engine. I don't want to make things any worse than they already are. The other thing is as I pull the plugs out, I'm going to be getting some clues. The fact that this plug is sort of dark, darkish color, almost like a charcoal color, gives me the indication that this engine has not been run long enough to have the plug reach its self-cleaning temperature. If this gets really bad, it's referred to as carbon fouling. And the plugs, when they come out, should be kind of like a whitish, like almost like a biscuity color, like the color of a, well, like a sandwich biscuit or something like that. The other thing I want to do is I want to make sure that I keep these in order because I can gather clues by that in terms of my diagnosis. So this is number 1. Put that right there. Going to number 2. Yeah, take a look at this. See this plug? It looks nothing like the plug I just pulled out, and it smells like gasoline. What I got is I definitely have some difference in color. Now, this tells me that if it smells like gasoline, I could have a stuck-open injector, or I could have combustion not occurring in that cylinder because maybe there's internal engine damage, which takes me back to the fluctuating vacuum gauge. So we'll keep this guy as cylinder number 2, and we'll move on. Take a look at the other plugs as we pull them out. There's plug number 3, and that looks a lot like the first plug we pulled out. And then this is plug number 4, and that plug also looks pretty much like 1 and 3. So this cylinder right here too is definitely my suspect cylinder. Now, the next step I'm going to do is I'm going to do a compression test. And the basic rules of a compression test are, is first of all, I don't want the ignition on. I actually have to disable the ignition coil if I'm going to use the ignition key. And I'm going to unplug my fuel injectors back here to make sure I don't have any fuel spray into the engine while I'm cranking it. Now, I don't have to really worry about that because I'm going to be using this remote starter switch, which I have hooked up. But if I were to use the ignition key, I'd also definitely want to make sure I disabled my ignition system. If not, I'd get shocked, and that won't feel good. And more importantly, aside from me getting hurt, I also run the risk of burning out the computer in the car because running the ignition system open can cause a surge of electricity to go back and actually fry the computer. So I'm going to make sure that doesn't happen. Plug this line back in. All right. The next thing I have to do is I have to make sure that I get a screwdriver and I block the throttle plate open. I want to make sure that I hold that throttle plate open while I crank the engine. And I'm also going to go get a booster pack for my battery. I have to make sure that the engine cranks at the same speed for each cylinder so I get a consistent reading. So let me get those tools and I'll be right back. So I'm going to take a screwdriver and I'm going to block my throttle plate open. And that's important to do because I want to make sure that I hold the throttle plate wide open so that way as I crank the engine I get a good gulp of air into the cylinders. It's an important step. You shouldn't forget it if you are doing a compression test. The other thing I have is I have a booster pack right here. And what I'm going to do with this is hook it up to the car battery. That way I have a good power source to keep the starter spinning at a constant speed while I do my compression test. All right, so now that I've got my engine all set up, what I'm going to do is I'm going to take my compression gauge and I'm going to thread it into the first spark plug hole. So a couple important things to keep track of when you do a compression test. Normally I'd write down all the numbers. Now on a 4-cylinder it's not too hard to remember all the numbers that you get, but when you do something like a V8 or a V6 or a V12 or a V10, it's a good idea to have a notepad handy so you can keep track of the numbers that you get when you run this test. The other thing is the test is an interpretation. Manufacturer of this car says that the minimum compression spec is 120 psi. So that's a minimum number I'm looking for each cylinder. But really, when we do a compression test, what we're looking for are values within 10% of each other. So when you do a compression test, you actually have to do it on all the cylinders at the same time. You have to take all the spark plugs out because cylinders actually can leak into one another through that head gasket. So let's see what we get when we go through here and do this, when we run our compression test. I'm going to double check first to make sure my ignition key is out of the ignition. And it is out of the ignition. And I'm ready to run my test. Now my gauge hooks up with a collar to the port where I plug it in. There's no tool, I just use the torque of my hand to actually tighten this down. And there's a thumb release, a pressure release on the side of the gauge. I have to make sure I don't have my thumb on that as I crank the engine over. So I'm going to crank my engine over and look at my gauge and see what I get. I'm going to crank it 4 times. You'll hear the engine turn over 1, 2, 3, 4. And that final gauge reading is what I'm going to get out of the cylinder. So, you like that jump? Yeah, I forget about how loud that can be. Let me try that again. So let me take a look at my gauge and let's see what we get. And what do I got there? I got about, looks like almost 200 psi. Now that's pretty good. If the manufacturer says the minimum was 120, almost 200 is great. If I have really high compression on all my cylinders, what that can indicate is that I have carbon buildup inside the engine. Generally, carbon buildup is going to lead to a possibility of the engine actually running too hot or overheating, possibly failing an emissions test. It's not really going to affect necessarily how the engine starts and runs, but it's something to watch out for, and it's interesting to see how high it is on this engine. This is one of our school cars, and we don't drive our cars here at the school. We run them in class, but we don't take them out on the highway and blow them out like you would with your personal car. So I'm not surprised that there's some carbon buildup in here, but let me release this and we'll go on to cylinder number 2. And here we go with cylinder number 2. That doesn't sound too good, does it? And you can hear that the engine doesn't sound like it's doing anything with cylinder number 2. In fact, it's just freewheeling, and I have absolutely no compression on my gauge. That's a problem. That means that cylinder number 2 has no compression. Cylinder number 2 is that on the compression stroke, nothing is happening. So that means that the air is either not getting into the cylinder, or the air that we're getting into the cylinder isn't able to be contained in the cylinder, and we're losing some of that air. One of the tricks that we can do at this point is we can actually take a little bit of oil and pour it into the cylinder and then rerun the tests. The idea is that while the oil sits on the head of the piston, which is basically the floor of my combustion chamber, if those rings are bad, the oil is going to help seal those rings a little bit, and I should get the gauge to go up. If I don't get the gauge to go up, it means that either the intake valve or the exhaust valve, or possibly the head gasket, is at fault, or I have a major failure on the cylinder with the rings or the head of the piston. So let me get some oil and we'll take a look at that. So this is my oil squirter. When I squeeze the trigger, it puts out about 1 tablespoon of oil. It's important at this point to realize that you don't want to flood the cylinder with oil. I just want to put a couple squirts in there, wait a second, and then rerun the test. So I'll give this a shot. There's 1, and there's 2. Wait a second. And right now the oil is running down the inside of the cylinder. Hopefully it's sealing things up. If not, we're going to see what we get. That oil made absolutely no difference whatsoever. So that means that the problem in cylinder number 2 is either the intake valve, the exhaust valve, or there's a catastrophic failure in that cylinder. So at this point, we're just going to move on and we'll check cylinders 3 and 4 just to make sure that there's no issues with them. There's a possibility, if it was the head gasket that had failed, that cylinder 3 and cylinder 2 could actually be leaking compression into each other. So I want to make sure that I check cylinder 3 before I go on with the rest of my diagnosis. Yep. And cylinder 3 got to 210 psi, definitely within 10% of cylinder number 1, which was 200 psi. So we'll vent that, and because it just takes a second, we'll do cylinder number 4, and that way we'll have a good baseline across the board. Yep, and 210 again. So cylinders 1, 3, and 4 have excellent compression. Cylinder 2 has no compression. So at this point, the news isn't good. We know that there is definitely a problem with the internals of this engine, and specifically, it's either with the, most likely with the valves on cylinder number 2. But I can still do a little more diagnosis. If I were going to tell a customer exactly what the problem was at this point, they're looking at an expensive repair bill, so I want to give them the most accurate diagnosis I can. So the other tool that I'm going to use now is, now that we know that cylinder number 2 has a problem, is we're going to use our cylinder leakage tester, and I'm going to hook up a compressed air line to this. What I have to do first, though, is there's another gauge that I put in here. What I have to do is I have to bring that cylinder number 2 to top dead center. And I have to make sure that both my intake and exhaust valves are closed. So what I have is I have another piece that looks just like it's part of the compression tester. I'm going to screw this in. But it has a whistle attached to it. And when we hear the whistle, what I'm going to do is I'm going to stop turning the engine. Now, my whistle is this little guy right here. And what I'm going to do is I'm going to take a breaker bar, and I'm going to go down onto the crankshaft of the engine, and I'm going to manually rotate the engine. And when I hear the whistle start to whistle, I'm going to stop rotating the engine. Now the whistle, when I hear it, means that both my intake and exhaust valves are closed and they should be sealed, and also the piston is on its upward stroke. So let me get that done. Okay, so I got my whistle, and I'm going to hook up my compression gauge, my cylinder leak down tester, and get this set up. And I'm going to blow air into the cylinder. So what I have now is I have some compressed air that I'm going to force into the cylinder. Now as I do this, I'm going to listen specifically for a couple things. If I hear air hissing out of the tailpipe of the car, it means an exhaust valve is stuck open. If I hear air hissing out of the throttle body, it means that the intake valve is stuck open. And I'm going to do two things. I'm going to take off the oil cap. If I hear air hissing out of here, it means my rings are damaged. And I'm going to take off the radiator cap, And if I see bubbles out of my coolant, it means my head gasket has failed. So let's hook it up and see where we have our leakage and how much leakage we have. And right here, while this is running, you can see the gauge immediately went to almost the red zone of my tester, which means I have pretty much high leakage. I have a high cylinder leakage now. I don't feel any air coming out of my oil fill cap. I can put my hand over it. I don't really hear any change there, so I know that the rings are okay. And I can see over here in the radiator, I don't have any bubbles. I don't hear any bubbles coming out of my coolant. So that means it's either out of the intake manifold. So let me tip the screwdriver out. I don't really hear any air changing there. So what that probably means is that my air is escaping out of my tailpipe at this point. And that would lead me to a problem with one of the exhaust valves in cylinder number 2. I could go back and I could listen to that, and I'd probably hear or feel a little bit of air. The air that I'm pumping into this is basically leaking in through this hose, going into the cylinder, and then it's forced out through the exhaust manifold as the system's pressurized. So what I'm going to do now is I'm going to go back and I'm going to use that borescope, and we're going to look inside the cylinder and see what we find in terms of a possible fault. Now, generally when a shop does this, if it's a 4-cylinder engine, you can see that it doesn't take a real long time to do this test. Most shops will charge you an hour, which is a very fair labor rate for base engine diagnostics like this. The more cylinders the engine has, or the more difficult the cylinders are to get to, the longer that test can take. So if you had something like a V8 or a V6, where maybe 4 of the plugs are very hard to get to in the back of the engine, this test could actually take possibly 2 hours to do. So let me get the borescope and we'll take a look inside the cylinder and see what we find. So what I have on the borescope is I have an angle adapter. And what this is going to do is it's going to allow me to look at the sides of the cylinder walls. It should also allow me to see the intake valves and the exhaust valves and see if we have any damage or if anything's stuck open. So let's take a look. Going to record. And going down through the inside here and making my way down inside the cylinder. Let me clean this guy off. So there's the threads on the spark plug. Right down there, that's the threads on the spark plug. So now we're inside the combustion chamber. And can I see anything going on inside here? Let's twist this guy around. Pull this angle adapter off. And it's hard to see. What I'm looking at right there is I'm looking at the head of the piston, and I can see all that oil that I put in there when I did that wet part of the compression test. It didn't change much. So that actually looks okay. I don't really see any damage here on the sides of the cylinder walls. They look okay. I don't see any scoring or damage. We'll pull this out and we'll put our angle adapter back on. We'll see if we can see anything. And taking a look. Turn this around. And right there, that line, oops, that line right there, that is the lip of my exhaust valve hung open. And that shouldn't be hung open. That guy should be closed. It should be sealed up at this point. So that tells me that one of the two exhaust valves on cylinder number 2 are stuck open, just like our tests showed us. So this engine is unfortunately going to probably have to have the cylinder head examined and come off. And at that point, we'll be able to come up with a full workup of exactly what it needs. But it needs more help than we can give it right now. I'm Dan Reed. Thanks for watching. Drive safely. 1, 2, 3. Hi, I'm Dan Reed with the Community College of Philadelphia. Welcome to Car Corner. Is that the normal intro? That sound okay? It seemed really short. Am I at 59 minutes yet? Okay. I see those valves open on the inside. I'm gonna do this. I'm gonna present here, and I'll just bring the crap over. Is that easier? Yeah, I sometimes think that works best. And I'll make sure I don't go like this while I'm trying to. Yeah, that's. Stop moving it. All right. Just keep going.